Hi, I'm Dr. J. Tori, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the hysteresis curve. So, in this topic, we are going to cover the hysteresis, and then we are going to explain the diagram of hysteresis curve, then soft magnetic materials, and then hard magnetic materials. Lastly, differences, and then we are going to see the references which are used in the hysteresis topic. So, hysteresis. So, in this hysteresis, when a specimen of a ferromagnetic material is placed in a magnetic field, the specimen is magnetized by induction. So, we are taking a specimen of ferromagnetic material, and this material is placed in the magnetic field. So, how the magnetic material, ferromagnetic material, is responds when it is placed in the when it is placed in the magnetic field. So, when a specimen of ferromagnetic material is placed in a magnetic field, the specimen is magnetized by the induction. So, as the magnetic intensity H is varied, the flux density B in the ferromagnetic material does not vary linearly with the H. H is nothing but magnetic intensity. So, H is the magnetic intensity. So, and then capital B is the flux density. Okay, so as the magnetic intensity H varied, the flux density B in the ferromagnetic material does not vary linearly with the H. So, the variation in B with variation in H is shown in this diagram. So, here we are taking H magnetic intensity along x direction, and the magnetic induction B is taken along y direction. So now, this specimen of ferromagnetic material placed in the magnetic field. As we are varying the magnetic intensity, how the flux density B can be varied. So, through this diagram, we are going to analyze the ferromagnetic material in the magnetic field. So, the point O represents, here in this diagram, the point O represents an initially unmagnetized specimen. So, at point O, the specimen is unmagnetized, that is, magnetic intensity is 0. At point O, the magnetic intensity is 0, means that magnetic field is absent at point O. So, there is 0 magnetic intensity at point O. The specimen is unmagnetized as 0 magnetic intensity, as there is 0 magnetic intensity. As H increased, when H is increased, B also increases. So flux density also increases, but it is not uniformly. And a point such as A is reached. So when magnetic field is increased, B flux density also increases, but not linearly. So here it increases non-uniformly and reaches point A and reaches to point A. If H is now decreased, so magnetic field intensity is decreased, then flux density also decreases, but not sudden decrease in the same path where it is increased, but it is taking another path and reaches point B. So, when applying magnetic field intensity, the specimen's flux density is increased and reached to a point A, and then if we decrease the magnetic field intensity, B flux density also decreases following the path A, B. Following the path A. So here B lags behind H. B lags behind H. So that is, when H becomes 0, B still has a value equal to OB. So here at a point B, the magnetic intensity is 0. The magnetic intensity is 0, but the flux density does not become 0, but it has some value. So the flux density is equal to, that value is equal to OB. This value is equals to OB. So this magnetic flux density remaining in the specimen in the absence of any external field is called residual magnetism. So the power of retaining this magnetism is called a retentivity or a remanence of the specimen. Retentivity or remanence of the specimen. So thus, the retentivity BR of a specimen is measure of the magnetic flux remaining in the specimen when the magnetizing force is removed. The retentivity BR of a specimen is a measure of magnetic flux remaining in the specimen when the magnetizing force is removed. And now, if the magnetic intensity H is increased in the reverse direction, the flux density value furtherly decreases, still lagging behind H, and become 0 when magnetic intensity has a value equal to OC. So, if the magnetic intensity H now increases in the reverse direction, so H is increasing in the a reverse direction. In the reverse direction. So what happened? The flux density in the specimen B furtherly decreases from the state of lagging behind H. So here at point B. So at point B, we are furtherly increases the magnetic field intensity H in the reverse direction. The value of B further decreases and becomes 0. So at point C, the magnetic flux density B becomes 0 when H has a value which is equals to OC. Okay, so when H becomes 0, then flux density have value that is BR is equals to OC. Sorry. When H have some value in the reverse direction, then the magnetic flux density has the value 0. B becomes 0. Okay. So, if the magnetic intensity H is increased in the reverse direction, B furtherly decreases from the state of lagging behind H at point B and have flux density 0 and become 0 flux density when H has a value equal to OC. This value of the magnetic intensity is called the coercive force or coercivity of the specimen. This value of the magnetic intensity is called the coercive force or coercivity of the specimen, that is HC. Thus, coercivity of the specimen HC coercivity of the specimen HC is a measure of the magnetic intensity required to destroy the residual magnetism of the specimen. So, whatever the flux density lagging behind H, that is when H becomes 0, we still have some value of a flux density called as retentivity or residual magnetism. So, to make this residual magnetism 0, we are furtherly increases the H so that flux density becomes 0 when H has some value which is equals to OC. So this magnetic intensity is called a coercivity. So thus, coercivity of this specimen HC is a measure of the magnetic intensity required to destroy. So where the flux density becomes 0. So the value of flux density is destroyed and becomes 0. Becomes 0 at the HC. So thus, coercivity of the specimen HC is a measure of the magnetic intensity required to destroy the residual magnetism of the specimen. So how much magnetic field intensity is required to destroy the flux density? As H increased, H means magnetic field intensity increased beyond HC, the specimen is increasingly magnetized in the opposite direction. Increasingly magnetized in the opposite direction, and a point such as D is reached. So now H is increased beyond OC. So increased beyond OC, the specimen is increasingly magnetized in the opposite direction and reaches a point D. It reaches point D. By taking H back to its negative maximum value through 0 to its original positive maximum value, a similar curve D, E, F, A is obtained. So at this point B and E, where the specimen is magnetized in the absence of any external magnetic intensity. So at the point E and B, there is some flux density where H is 0. So that it is said to be permanent magnet. So at the points B and E, the specimen is magnetized in the absence of any external magnetic intensity, so that it is said to be permanent magnet. So it is thus found that the flux density B always lags behind the magnetic intensity H. So the lagging of B behind H is called hysteresis. So the closed curve AB, C, D, E, F, A represents a cycle of magnetization of the specimen is known as hysteresis curve. Hysteresis curve or hysteresis loop. Of the specimen. So the closed curve A, B, C, D, E, F, A is called as hysteresis curve or hysteresis loop of the specimen. Based on the area of the hysteresis loop, ferromagnetic materials can be classified into two types. One is soft magnetic material, another one is hard magnetic material. So these ferromagnetic materials, depending upon the hysteresis loop, can be classified into two types. One is hard magnetic material, another one is soft magnetic material. So when coming to the soft magnetic material, depending upon the size of the hysteresis loop, ferromagnetic materials are classified into soft and hard magnetic materials. The ferromagnetic material which are easily magnetized and demagnetized are known as soft magnetic materials. So coming to the properties of the soft magnetic materials, those soft magnetic materials shows a very deep, steep hysteresis loop. So that is, the loop will be so the curve of the hysteresis. So the hysteresis curve of the soft magnetic material is shown in this figure. So it has very deep, steep loop. So like this. Here the beer and here the hedges. And taking magnetic intensity along x direction. Okay, so soft magnetic materials shows very deep, steep hysteresis loop as shown here. The area of the loop is very small and hence they show high value of susceptibility and variability. Soft magnetic materials can be magnetized and demagnetized easily, and hence they show high values of susceptibility and permeability. Due to steep nature of the loop, it is clear that it has low value of coercivity. It exhibits low retentivity and it exhibits high resistivity, and then they require, soft magnetic materials require low magnetic field for magnetization. So because of easily magnetized material, that is soft magnetic materials are easily magnetized and demagnetized, so that low magnetic field is enough for the magnetization. When we see the examples, we can take iron silicon alloys, nickel iron alloys, iron cobalt alloys as a best examples. Coming to the applications, they are used in the electrical equipment and magnetic cores of the transformers. They are used in motors, relays and then sensors also. They are also used in the microwave isolators. When coming to the hard magnetic materials, the ferromagnetic materials which are hard to magnetize and demagnetize are known as hard magnetic materials. So they have some properties. So these hard magnetic materials are very hard to magnetize and demagnetize. They require high magnetic field for magnetization and also demagnetization. The corresponding hysteresis loop is very broad. So how the loop will be? So it is very broad. So very broad. Magnetic field intensity, flux density, here residual magnetization, here HC, coercivity of the specimen. So hysteresis loop of hard magnetic materials. So the loop, here you can see the loop is very broad, so that they require high magnetic field to magnetize or demagnetize. Hysteresis loss is large due to large area of the loop. They exhibit low values of susceptibility and permeability due to the broader area of the loop. They have high coercivity and retentivity. We can take carbon steels, tungsten steels, chromium steel, etc. for examples. And coming to the applications of the hard magnetic material, they used in making permanent magnets, used in DC motors and measuring devices. They are used in speedometers and sensors in the automobiles, motors, etc. So, these are the soft and hard magnetic materials. Coming to the comparison between soft and hard magnetic materials. So, soft magnetic materials can be easily magnetized and demagnetized, where in the case of hard magnetic materials, magnetization and demagnetization are very difficult. In soft magnetic materials, small magnetic field magnetizes the soft magnetic material since domain walls moves easily and reverse field. Large magnetic field is required to magnetize the hard magnetic materials since domain walls movement is very hard. Because of domain walls movement is very hard, so they need large magnetic field to magnetize the hard magnetic materials. It consists, that is, soft magnetic materials consist of a very steep hysteresis loop, whereas hard, it consists of a broad hysteresis loop. Soft magnetic materials, since the hysteresis area is very small, the corresponding loss is also small. In hard magnetic materials, area is large, so the corresponding loss is also large. Soft magnetic materials have large values of susceptibility and permeability, whereas hard magnetic materials have low values of susceptibility and permeability. Soft magnetic materials coercivity and retentivity values are small, whereas they are large in the hard magnetic materials. Soft magnetic materials are used in the preparation of magnetic core materials used in the transformers, electric motors, and magnetic amplifiers, etc. Hard magnetic materials are used in the preparation of permanent magnets, which are used in loudspeakers, microphones, magnetic detectors, etc. So these are the comparison between the soft and hard magnetic materials. So in the hysteresis is known that B is lagging behind H is the hysteresis. So in the hysteresis, firstly, we are placing the ferromagnetic specimen in the magnetic field. So when at a point O, when there is absence of magnetic field intensity, B also 0. When increasing H, B increases non-uniformly and reaches to a point A, then making B 0, H is decreasing, so when decreasing H, the flux density also decreases, but not in the same path as previous one, that is not in the OA path, but it takes another path from A and reaches to a point B, where here at point B, H is 0, but still there is flux density. So this is called retentivity or residual magnetism. Then H is increased in the reverse direction. B also decreases and reaches to C. So at the point C, it has some magnetic field intensity, but B becomes 0. So here the flux density is totally destroyed, called as the coercivity of the specimen HC. So coercivity of the HC. It is a measure of the magnetic intensity required to destroy the residual magnetism. So at the point C, the residual magnetism becomes 0, but there is some magnetic field intensity. Then H is increased beyond OC, the specimen increases, increasingly magnetized in the opposite direction and reaches to a point. By taking H back from its negative maximum value to original positive maximum value, it takes a path D, E, F, E. So at the points B and E, when there is a magnetic field intensity 0, we have some value, flux density. That still flux density is there. So at B and E, where the specimen is magnetized in the absence of any external magnetic intensity, it is said to be permanent magnet. So the lagging of B behind H is called hysteresis, and this closed loop is called the hysteresis curve or hysteresis loop. So this is all about the hysteresis, and the references for engineering physics by K. Tyagarajan, McNoyle Education Private Limited, New Delhi. Then a textbook of engineering physics which have been written by the M.N. Avdanalu, P.G. Shirsagar, publication of Chandred Company. Next, engineering physics, Dr. M. Armita, Anuradha Publications, Chennai. Engineering physics, P.K. Palisamy, 4th edition, Scientific Publications, Chennai. Modern engineering physics, Dr. K. Vijay Kumar, Dr. S. Chandralingam, published by S. Chandan Company, New York. So these are the references which are used for this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.